This paper addresses the simple foldability problem, which involves deciding whether a given crease pattern on a piece of paper can be folded flat through a sequence of simple folds. The authors focus on orthogonal crease patterns and examine different models for simple folds, including one-layer, some layers, and a layers folds. They also differentiate between assigned, unassigned, and mixed crease patterns, where some creases are assigned as needing to be folded mountain or valley, while others lack an assignment. The paper presents a comprehensive summary of prior results and new findings in Table 1, highlighting complexities based on various parameters such as the shape of the paper, the number of layers, and the nature of crease assignments. The authors provide new characterizations for when a 1D assigned or mixed crease pattern is flat foldable, adapting arguments from previous studies, Abid plus 04. For one-layer folds on rectangular paper, crossing creases cannot be folded, reducing the problem to 1D paper. The study also explores the distinction between finite and infinite simple folds, noting that this distinction only plays a role with arbitrary paper. No distinction can be made in the 1D case, and equivalence for rectangular paper is given by AdK 17, Theorem 8. The paper's new results include solving several new cases of the simple foldability problem, providing efficient algorithms for mixed crease patterns in 1D and 2D rectangular paper, and showing strong NP-completeness for mixed orthogonal crease patterns on 2D rectangular paper with some layers simple folds. In the context of unidimensional paper folding, this research introduces a novel characterization for flat foldability of assigned crease patterns. The new characterization is based on the concept of suspicious intervals, which are defined as interior intervals with flaps whose images in the folded state are strictly outside the image of the interval itself. An interval is considered innocent if the difference between the number of mountain and valley creases within it does not exceed plus or minus 1. The proposed theorem states that an assigned 1D crease pattern is flat foldable if and only if every suspicious interval in the crease pattern is innocent. This result is proven through a cycle of implications, demonstrating the equivalence of flat foldability under different models, including sequences of crimps and end folds, one and some layers simple folds, and general flat foldability. The paper also discusses the NP hardness of deciding simple foldability for some layers mixed rectangular crease patterns, as well as unassigned arbitrary finite crease patterns. These results build upon previous studies, such as the work by AAB plus 20 for a layers mixed rectangular crease patterns and AdK 17 for unassigned crease patterns. Furthermore, the paper presents a polynomial time algorithm for deciding simple foldability in the one and some layers models for 1D paper. This algorithm utilizes two fundamental folding operations, crimps and end folds. Crimps involve folding two consecutive creases with opposite orientations, while end folds involve folding a crease adjacent to an end of the paper. Both operations can be executed as one or two-layer simple folds, respectively, and preserve the single-layer property of unfolded creases. The paper concludes by noting that the only remaining unsolved case for orthogonal crease patterns is the infinite layers simple folds of assigned crease patterns on arbitrary paper. This highlights the complexity and depth of the problem space, underscoring the importance of continued research in this area. Here is a combined summary of pages 5 and 6 of the research paper. The authors consider a flat folding of a paper and restrict their attention to a suspicious interval and its flaps, adding a line segment connecting the two far endpoints. This forms a loop with one or two added creases, which are convex relative to the loop. The net turn angle of a non-intersecting closed loop is 360 degrees, implying that the loop must have two more convex creases than reflex creases. This leads to the conclusion that the interval is innocent. The authors then prove several lemmas relating innocent suspicious intervals to crimps and end folds. Lemma 2.2 states that if every suspicious interval is innocent, then some segment must be crimpable or end foldable. The proof involves considering a shortest segment in the crease pattern and the maximal sequence of equal-length segments containing it. If one end is an end of the paper, the incident segment is end foldable. Otherwise, the interior interval of equal-length segments is suspicious and thus innocent, containing at least two creases, including a mountain and a valley. Lemma 2.3 proves that performing a crimp preserves the innocence of every suspicious interval. The proof involves considering the suspicious interval after the crimp and its relation to the new segment created by the crimp. In all possible cases, the lemma shows that the suspicious interval remains innocent after the crimp. Lemma 2.4 proves that performing an end fold also preserves the innocence of every suspicious interval. The proof involves considering the case where the end fold is the leftmost crease and showing that the deletion of the leftmost segment does not affect the innocence of any intervals not containing the leftmost crease. The authors then use these lemmas to prove that if every suspicious interval is innocent, then there exists a sequence of crimps and end folds to fold the crease pattern. This completes the proof of Theorem 2.1. Finally, the authors discuss the application of their results to mixed 1D crease patterns, where each unassigned crease can be either mountain or valley. They define a valid assignment as one that results in a flat foldable assigned crease pattern, or equivalently, one where every suspicious interval is innocent. The paper discusses the problem of determining whether a mixed crease pattern on a 1D or rectangular paper can be folded flat using one layer or some layers simple folds. The authors provide an algorithm that, in polynomial time, determines the flat foldability of such patterns. They begin by defining suspicious intervals as those where the far endpoint of the right flap lies outside the image of the interval in the folded state, and similarly for the left flap. The authors then prove that the intersection of two suspicious intervals is also suspicious, and that assigning creases to make a suspicious interval innocent preserves the existence of a valid assignment. The algorithm proposed first finds all suspicious intervals, then processes each minimal suspicious interval I if I has an even number of creases. It assigns them to make exactly k mountain and k valley creases. If I has an odd number of creases, it assigns all but one crease to make k plus 1 mountains and k valleys, or vice versa, and leaves the remaining crease unassigned. This process is repeated until every suspicious interval has been considered, at which point all remaining creases are assigned arbitrarily, resulting in a valid assignment by Theorem 2.1. The authors show that this algorithm runs in polynomial time and thus proves corollaries 2.8 and 2.9, which state that given a mixed 1D crease pattern, we can determine in polynomial time whether it can be folded flat using one layer or some layers simple folds. They also extend these results to rectangular paper with mixed crease patterns in corollary 2.10, where an orthogonal crease pattern containing both horizontal and vertical creases is never flat foldable in the one-layer model. But a pattern with creases in only one direction is equivalent to a 1D mixed creased pattern and can be analyzed using the same algorithm. Here is a combined summary of pages 9 and 10. In the A-layers model of 1D paper folding, a polynomial time greedy algorithm is presented to solve the mixed crease pattern problem. A valid fold in 1D must fold each valley, respectively mountain, crease onto a mountain, respectively valley, or unassigned crease, or onto a point not interior to the paper. Equivalently, the paper can be reduced to a shorter line segment with fewer creases by discarding the shorter portion of the paper on either side of the crease. The simple greedy algorithm, which performs any valid fold at each step, fails in the mixed case because folding an assigned crease onto an unassigned crease effectively assigns it. A more refined greedy algorithm is proposed, where a crease is called plausible if it would be a valid first fold if every crease were unassigned. Lemma 3.1 proves that if there is a sequence of valid A-layers folds that folds the crease pattern, then there is such a sequence that folds the plausible crease with minimum distance to an end of the paper first. The proof of Lemma 3.1 involves considering the open interval centered at the plausible crease and showing that the first fold in this interval must be at the plausible crease. This leads to a refined greedy algorithm that repeatedly finds and folds, if possible, the plausible crease nearest an end. Theorem 3.2 follows, stating that there is a polynomial time algorithm to determine whether a 1D mixed crease pattern can be folded using A-layers simple folds. The algorithm's correctness relies on the notion of plausible creases and the properties of symmetric crease patterns. The reduction to a shorter line segment with fewer creases enables the greedy algorithm to succeed in the fully assigned and fully unassigned cases. However, the mixed case requires a more nuanced approach, which the refined greedy algorithm provides. In the realm of geometric origami, this research paper delves into the complexities of determining whether a mixed orthogonal crease pattern on rectangular paper can be folded in the sumlayers model. The paper begins by discussing a cubic time algorithm for checking the foldability of such crease patterns, which contrasts with the polynomial time algorithm available for the one-layer model. This algorithm iteratively identifies and checks plausible creases, either by folding them first or determining that they are not valid, thus preserving foldability. The paper then transitions to proving the NP-completeness of determining whether a mixed orthogonal crease pattern on rectangular paper has a simple folding in the sum-layers model. This proof builds upon the reduction from 3SAT developed by Akitaya et al., which involves creating a long strip of rectangular paper divided into a square grid of creases. Each section of the paper corresponds to a variable in the 3SAT instance, with the lower part containing valley creases for each occurrence of the variable in a clause, and the upper part containing mountain creases for each occurrence of the variable in a clause. A topmost section checks the satisfiability of the clauses, and assigned creases enforce the variable order. The paper also presents a lemma that demonstrates that whenever a simple fold is made in an orthogonal crease pattern with rectangular paper, if it is not in the same direction as the previous fold, it must be in a layers fold. This claim is proven through induction, assuming that the claim holds for all previous folds and then showing that it must also hold for the current fold. The paper concludes by using this lemma to prove the NP-completeness of the sum-layers model, as the instances described in the reduction never permit a folding other than the intended one, even when relaxing to the sum-layers model. In the context of the paper folding problem, the authors present a reduction from 3 partition to determine whether an unassigned or assigned orthogonal crease pattern on arbitrary 2D paper has a simple folding. This reduction applies to all 3 models of simple folds: one layer, sum layers, and a layers. The authors first discuss a bug in the previous assigned reduction by Akitaya et al. AdK 17, which reduces 3 partition to the assigned problem. The bug arises when the vertical position of the bar must align with the staircases in the cage, requiring folding of total length of segments in the staircase each time. However, there is an unintended folding that avoids vertically aligning the bar with each successive step of the staircase. To address this bug, the authors modify the construction by adding a new component called the tongue, figure 9. The tongue is a long horizontal rectangle that extends from the bottom of the bar to the top of the cage, with crease spacing equal to the width of the adjacent vertical column. The addition of the tongue ensures that the bar must vertically align with the staircases in the cage, as intended, and thus fixes the bug in the previous reduction. The authors then adapt the proof to the unassigned case. In this model, the reduction still applies, but it is more complex due to the lack of pre-assigned creases. They show that the reduction still demonstrates NP hardness even in the sum-layers model, as every no instance in their reduction is not foldable in the sum-layers model. This is achieved by ensuring that the number of mountains and valleys differ by exactly 2 around any vertex, making it impossible to fold the no instance in the sum-layers model. The paper also discusses the finite folds required for the reduction, which can be achieved by adding an extra gadget, figure 10, that enforces the desired folding behavior. This gadget consists of a series of alternating mountain and valley creases, with the number of mountains and valleys differing by exactly 2 around any vertex. The gadget prevents the unintended folding that bypasses the vertical alignment between the bar and the cage, ensuring that the reduction remains valid in the unassigned case. In conclusion, the authors have successfully modified the previous reduction from 3 partition to the paper folding problem, addressing the bug and adapting the proof to the unassigned case. This demonstrates the NP hardness of determining whether an unassigned or assigned orthogonal crease pattern on arbitrary 2D paper has a simple folding, applying to all 3 models of simple folds. The paper discusses the NP-completeness of determining whether an assigned or unassigned orthogonal crease pattern on arbitrary paper can be folded in the one-layer, sum-layers, and a layers models. It presents 2 main reductions: the assigned reduction and the unassigned reduction. In the assigned reduction, a modification to the proof from AdK 17 is shown, involving the addition of a second arm above the wrapper to prevent bad folding behaviors. This modification ensures that the bar passes through the cage at each step, checking for the 3 partition instance satisfaction. The unassigned reduction modifies the assigned reduction by using unassigned orthogonal creases and particularly shaped paper to achieve NP hardness. The paper highlights novel ideas in folding patterns and their implications on computational complexity, providing a comprehensive analysis of folding behaviors and their relationships with computational problems. The research paper presents a novel reduction from the three-partition problem to the assigned orthogonal crease pattern simple foldability with arbitrary paper. This is achieved through the introduction of a new structure called the cactus, which replaces the wrapper in the original reduction. The cactus consists of short branches that ensure creases are folded in increasing order, starting with C0. These branches are aligned so that when a crease C is folded, the previous branch I1 aligns with the next branch I+1, making it impossible to fold C1. This forces the folding to respect the intended order on the cactus. In Figure 10, the intended folding sequence for the new reduction is demonstrated, including the addition of arm2. This sequence involves crimping variables to change the height of the bar by 2t, folding along the rightmost wrapper crease around the column, fitting the bar through the cage by folding the bar to the left along the next wrapper crease, and repeating this process until n3 triples have been checked. The cactus construction, shown in Figure 11, enforces a right-to-left fold order due to the arms sticking out of the cactus. For instance, if crease C1 is folded before crease C0, it causes A2 and A0 to lie on top of each other, preventing C0 from folding without A2 and A0 colliding. This ensures that the folding must fold C1 before C, respecting the intended order on the cactus. Arm1 plays a crucial role in enforcing that all creases on the wrapper are folded in the same direction, assuming the order of these creases is already forced. Specifically, if the unassigned creases of the wrapper are folded from right to left, the only way for arm1 to never collide with anything is for those creases to be either all mountain or all valley creases. This is necessary to ensure that the cactus functions correctly and maintains the intended fold order. The authors utilize arm1 to ensure that creases in the cactus are folded with the same assignment, thereby proving NP hardness for unassigned 45 degrees creases. This construction is independent of the one-layer, some layers, or a layers model, as every fold is a one-layer fold. The paper highlights 6 open problems, with a focus on infinite layers simple folds of assigned crease patterns on arbitrary or orthogonal pieces of paper. One approach to proving hardness is to modify the reduction from the rectangular mixed assignment problem, removing a small neighborhood of paper around each unassigned crease. However, this process often disconnects the paper, making it difficult to overcome this barrier. An alternative approach is to reduce to the rectangular fully assigned problem, which is solvable in polynomial time. The authors propose expanding the piece of paper to its rectangular bounding box and extending all creases into the bounding box as unassigned creases. However, assigning these extended creases in a way that makes the crease pattern foldable with infinite layers folds remains an open challenge. Figures 12 and 13 demonstrate the complexity of this problem, showcasing how seemingly safe creases can render the pattern unfoldable. Finally, the authors acknowledge the contributions of their colleagues and provide a list of references that have influenced their work.